Hi everyone, our project is behavior cloning for avoidance direction selection. The core question is whether a compact neural network can replace an LLM-based lambda controller while keeping the same DP planner. Here is a roadmap. I will briefly introduce the motivation, our main insight, and the problem formulation. Then my teammates will cover the implementation and results. This slide starts with the motivation section. In dynamic obstacle avoidance, there are two coupled decisions. First, the controller decides which side of each obstacle the ego vehicle should pass. This is represented by a binary lambda value. Then the DDP planner uses those lambda values to optimize the continuous trajectory. LLMs can make these high-level decisions, but they are not ideal for real-time planning. They require more model serving, text generation, JSON parsing, timeout handling, and the fallback logic. So our goal is to keep the planner fixed and replace only the lambda source. Our insight is that lambda selection may be mostly geometric. Instead of using text generation, the neural networks directly predicts lambda from compact features like relative position, lateral velocity, and lane information. This is our system pipeline. The traffic scene goes into a lambda controller. The corridor bounds are built, and the same DDP planner produces the trajectory. Only this lambda controller block changes. DDP LLM will use the phi 3+5, and while DDPN use our neural network. Formally, each planning step is a variable. Each planning step is a variable size binary prediction problem, and the controller observes the ego vehicle and the nearby obstacles, then outputs the lambda value for each obstacle. These lambdas define which side becomes infeasible, like this. And finally, both controllers use the same corridor constrained DDP planner, so our comparison isolates the high-level lambda decision rather than comparing two different planners.
We use DDP-LLM as the baseline controller, and we also used it to collect the data we needed for training. As for the language model, large language model, we used a local model 5756, and we locally hosted it on a server so that we could use a different Python version 3.10 while keeping the Sumo Carla co-simulation in Python 3.7. When the output format doesn't match, we use the rule-based fallback for the lambda vector. And after collecting the data, we created a GUI tool to help annotate the data. And since we had large disagreements over corner cases, we ended up having each person annotating the entire dataset that we created, and then used the agreement weights during training. But we didn't use the weights during validation, where we treated the majority vote just as the ground truth. And here are the features that we selected for the final model, and we also had self-attention blocks so that each obstacle can attend for all other obstacles in the same scene and have better context when predicting the lambda values for each obstacle. And as it turns out, the engineered features such as clustering directions actually performed worse than models with just raw geometric features. And so we also compared the two controllers in the simulation. The settings are all the same for the two controllers. The only intended difference is the source of the lambda. In our simulation, Carla on the website is for rendering only, and Sumo on the website is for the actual physics.
Main closed-loop comparison. Overall, the neural network performs better on the most key metrics like the DDP cost, patience, lane changes, job, while has higher average speed and much lower compute time. On the other hand, the LLM slightly does better on travel time, fuel, and CO2. So the conclusion is that the neural network is promising, especially for smoothness and efficiency, but not better on error metrics. And here's the graph of the lifecycle level driving metrics. This is showing that not in every cycle the neural network does better than LLM, but still favor overall neural network. For the timing metrics, the neural network removes the LLM serving, text generation, JSON parsing, and fallback path. So the CPU drops and the summed walk clock average also drops. This matters because this is a repeated replanning problem. a smaller neural network controller is much more practical inside a real-time controller. Our interpretation is that the lambda selection is most learnable from complex geometric features. The neural network is not learning the full driving task, but it learns high-level binary size choices. For the limitation, this is final match round with limited labels, one route, and one traffic setup. So LN still slightly wins on some efficiency metrics. For the key takeaways, firstly, behavior cloning can replace LN lambda model while keeping the same planar interface. Secondly, the neural network gives a strong practical benefits like lower overhead and better on the cost lane changes, collisions, and speed in this round. Third, the neural network is promising, but broader tests is needed.